This video is not suited for photosensitive viewers. I'm sorry, kings, queens, and regents. I'll make it up to you next time. Life. What is it? Does it end? Are we alive? All of these questions have answers. The one we're still pondering, though, does not, which is why we're still pondering it. Where does life come from? If we trace evolution back far enough, eventually something or some things must have come first. But how could something so complex as life possibly start from nothing? This video will not answer that question. However, you may have noticed that none of the cells in these clips are real. In creating them today, we will see how a surprisingly diverse complexity can arise from very simple beginnings. So let's get started. Our search for life begins, fittingly, with the game of life. Not the Hasbro board game about exploiting your children and dying rich. No, today we're talking about Conway's game of life. John Conway was a British mathematician who wanted to show how simple rules can form complex systems. To that end, he proposed the following game. We'll start with a grid of tiles that are either alive or dead. Each round, every tile counts up its living neighbors, including diagonals. If the tile is on the edge of the grid, this neighborhood wraps around to the other side. Let's fast forward through the count and get to stage 2. Stage 2. Now we'll update the grid by the following rules. A living tile with fewer than 2 neighbors dies by underpopulation. A living tile with more than 3 neighbors dies by overpopulation. And a dead tile with exactly 3 neighbors comes to life by the power of thruple love. Otherwise, no change occurs to a given tile. So let's run that through and see how our grid changes. Okay, lot of death, but we did have 2 new tiles come to life. I guess a certain amount of loss was to be expected with that starting config. Let's run for a few more generations and see how our system evolves. Our ecosystem died after 9 turns. That's pretty fast, so this really was a lossy pattern. Now that we know the rules of the game, we can write a bit of code to bring it to life. This function will update 1 cell on the grid. It loops through the cell's neighbors with a bit of extra logic to handle wrapping at the edges of the screen. If the neighbor is alive, it adds 1 to a running count. Then, once we've checked all neighbors, it passes the total count through the rules that we laid out earlier. If a living cell has 2 or 3 living neighbors, we'll give our next generation a value of 1, meaning alive. Otherwise, we'll give it 0, meaning dead. We'll also give dead cells a chance to come to life by the reproduction rules that we outlined earlier. Whatever value we end up with, we'll then send forward to our next grid. Once we've run this function on every cell, we'll have completed 1 turn of the game of life. The one caveat is that, well, this was my first time working with a compute shader, so it came out a little red. Welcome to Conway's game of life on the Nintendo Virtual Boy. It comes with a few cool features, like a frame rate slider and a drawing tool. We'll explore those more in a second, but for now, let's just try running our code on some random noise for our first real look at the game of life. Immediately, the board descends into chaos. Each update follows a rule that we can understand, but not easily follow. That familiar unpredictability is what makes the results so compelling. It's also what makes them look vaguely organic, like bacteria in an 8-bit petri dish. Unfortunately, it collapses past those 8 bits. The biggest limitation of Conway's game is that patterns only emerge on small scales. Anything larger requires a human touch, and it ends up looking more mechanical than lifelike. This is just an inherent consequence of Conway's rules. So long as each cell only looks at the 8 cells directly around it, it's nigh impossible for anything interesting to form on a much larger scale. So, let's break the rules. Instead of our square 8-cell neighborhood, let's try using a circle. our circular neighborhood will include every cell whose center lies inside of the circle. This has a big advantage in that we can now freely control the size of our neighborhood and make it as big or small as we want. For now, let's go out to a 4-cell radius. Just like with our old square neighborhood, we'll first count up all the living cells in our circle. So let's randomize the board real quick so we can see what that looks like. Now, what do we do with all these tiles we counted up? Previously, we followed these rules. These won't really work for a variable-sized neighborhood, so let's generalize. 2 cells was 25% of our 8-cell neighborhood. So let's set our underpopulation threshold to occur when 25% of our new neighborhood is alive. 3 cells is 37.5% of 8, so we'll set overpopulation to be 37.5%. Thruple is a little trickier because it's a fixed number, so my compromise was to set it between 30 and 40% and just hope for the best. With our rules squared away, I updated our Game of Life code to reflect our new system. We'll now loop through all of the x and y values that are less than the circle's radius away from our cell, and run a distance check to make sure they're really inside of our circle. We'll keep a count of the total cells in the circle and a separate count of just the living ones. Dividing these counts together gives the ratio of living cells to total cells in our neighborhood. We'll then plug that ratio into our new update rules. And that's all the changes to our code, so let's return to our game. Inside of our game scene, I've added a slider to control the neighborhood's radius, visualized in yellow. I really want to see our new emergent patterns, so I'll stop yapping and just run it. Let's see how we did. Oh. Well, let's run that back with a much slower frame rate. Okay, so we are getting new patterns, they're just dying really fast. It turns out that you can't just scale up Conway so easily. So, we tinker. I made this parameters panel so that we can quickly tweak aspects of our system and experiment. The survival range represents the under and overpopulation thresholds from rules 1 and 2, while the reproduction range represents rule 3. I also added a new variable called random fill %, which controls how much of the grid starts out alive. Since our previous grid died too quickly, let's try a larger survival range, and let's keep the random fill % low so that it starts inside of our survival range. That was better for sure, but the system still stopped. Let's nudge the reproduction rate and see what happens. Whoa, this is definitely better. Lest we forget, we switched to the circular neighborhood to see if our system would form large-scale patterns. And so far, it looks like we've succeeded. So let's push it a little further. Let's raise the neighborhood radius to about 7. And it looks like we may have outgrown our resolution, so let's expand our grid to 1400 by 1000 cells, 400 times as big as we were before. Cool, so we're still a little chaotic at large scales, but I do feel like I'm seeing some structure here. It may be the low frame rate, but it looks like there are particles moving in a large circle around the grid. Is that just me? I'm very curious if that's real, so let me know if you see it too. In the meantime, I'm going to tinker around and see if I can find anything else of interest. Alright, I spent a few hours tinkering and I learned a lot about this system. The first thing I discovered was that most settings result in noisy patterns like the one that we saw before. However, when I set the reproduction range to be super wide, this happened. Not at all lifelike, but damn, pretty cool. I also found this pattern, which at a glance just looks like more random noise. But when I refreshed the grid a few times, this bubble formed. It turns out that this system is so dependent on its initial conditions that the various different random starts that I generated gave wildly different results. Case in point, here's another version with the same settings where 2 of those bubbles formed with very different internal structures, and then collided. So from here on out, I made sure to run every parameter set multiple times just to try and find rare patterns. And eventually, that paid off. I found a set of parameters that form small amoeba-like bubbles. These bubbles move around and interact with each other, but don't spread out to fill the whole grid. If Conway's game formed 8-bit bacteria, this felt like the next-gen console. They're still far from alive, but to my eyes, this is the most lifelike system that we've seen so far today. To celebrate that, I decided to give them a name. Their Latin name will be Parvuli Quosum Veni, or Little Guys Who I Found. And with this groundbreaking discovery, I feel like we've exhausted this iteration of our life system. So let's improve on it again. The main thing that's holding us back right now is how our tiles change so rapidly every single frame. And that's bound to happen with only 2 board states, since any change will be a full shift from alive to dead. So to smooth our system out further, we'll let cells exist somewhere in between life and death. Our system must learn to be mostly dead. We've already laid the foundation for this change. Under the hood, our code thinks of alive as a value of 1 and dead as a value of 0. It doesn't care if the cell takes a value in between those, but we will need to rethink our update rule. Currently, when a cell dies, its value goes from 1 to 0. When it comes to life, it goes from 0 to 1. That means that we could reimagine our update as a kind of math function, one that adds to the value of cells who should be coming to life and subtracts from cells who should be dying. The ideal function for this is a Gaussian. Gaussian functions form bell curves that go from 0 to 1 and then back again. By stretching our curve up and then moving it down, that becomes -1 to 1. The positive part is both our survival range and our reproduction range. We can adjust that range with these 2 parameters, mu, which moves the curve left and right, and sigma, which controls its width. Playing with these, we can align the Gaussian with the update rules from our Quosum Veni. Now our growth function is positive when our living cell ratio is between 14.4 and 33.2%, and otherwise will be negative. Back in our code, we'll now plug our living cell ratio into the Gaussian to get our growth function. To make doubly sure that we don't grow too much, we'll also multiply the growth by a very small factor called dt. That means that each cell can only grow or shrink a little each update, so the system won't wildly grow or die. Finally, if the new value is larger than 1 or smaller than 0, we'll clamp it into place. That should do it for our code, so let's return to the game scene. Back in our game, the board now holds many shades of red, with brighter shades corresponding to aliver cells. I've got the parameters set to the growth range from our Inveni, so let's run it. Pretty quickly, this system reached a stable configuration and just stopped moving. This turned out to be the overwhelming trend for the Gaussian growth function. The systems stabilize into a fixed pattern and just stay there. This seemed to happen for every combo of mu and sigma that I tried, and while the patterns were cool, they really weren't what I was looking for. Then, something happened while I was exploring this somewhat creepy looking pattern. After it stabilized, I tried turning sigma down, almost to 0, and ran it again a few times. And then, this guy appeared. This guy is awesome. It maintains a consistent shape even when moving and turning, and it even interacts with the user if you draw cells around it. I spent quite a while playing with this creature, and determined that it is in fact a little guy. Thus, it becomes the second member of the Parvuli genus. I've named it the Parvuli Dosum Veni. The Dosum Veni is the only individual creature I discovered in this Gaussian growth system. That speaks less to how many creatures there are, and more to how hard they are to find. The Dosum Veni was so rare that I kept losing it, even just while recording this video. They'll look a little different in each of these clips because I kept rediscovering them with slightly different parameters. I suppose that would make each clip a different phenotype of the Dosum Veni, although I'm not sure if it works that way. Regardless, as a species, they're not the most survivable bunch. When 2 Dosum Veni get near each other, they seek each other out and then merge to form one new Dosum Veni. That's beautiful, but it's also not a great strategy for long-term species survival. I also noticed that the Dosum Veni seemed happier moving in cardinal directions. This made sense given that our underlying grid is made of squares, but it made me wonder if they might fare better on a hexagonal grid. Or would they even exist anymore? Well, only one way to find out. So I retooled the whole project to use a hexagonal grid. This was way more math than I expected, and it required me to fully rewrite the rendering logic and the neighborhood logic. I'm glossing over a lot here for reasons that'll soon become clear, but if you do want to learn more about hex grids, I highly recommend this website, Without it, this manic little side quest would have been completely impossible. But after a week of debugging, we ended up here. It's kind of hard to tell at this resolution, but if we zoom in, those are indeed hexagons. So we have hexagons. Do we have a Dosenveni? Yep, it's entirely unchanged, except that now it likes moving on diagonals. It's good to see you too, little guy. It turns out that all of our patterns were functionally the same on a hexagonal grid, and I later ended up reverting back to squares to make the programming a little easier. Although this is a bit disappointing, it's actually quite useful to know that the grid shape doesn't meaningfully affect our results. I've seen papers float the idea of hexagonal grids, and it's useful to know that, no, it's not a useful avenue to explore. Also, the way I set up the hexagons let me do this. The height of each hexagon corresponds to its cell's value, so aliver cells are taller. If we refresh a few times, we can find our hexagonal Dosenveni but in 3D. In 3D, we can see that the back half of the Inveni has a slightly higher aliveness value than the front. As it loops around the edge, we'll also get a better look at its little feet kicking. These feet, or fins, or whatever they are, have emerged in every Dosenveni to date. I call them fins, but that's probably just my human bias. I have no idea if they're actually part of this creature's locomotion. The difficult part of studying creatures like the Dosenveni is that I can't really experiment with them. I can only observe them and their variants. Variants like this horrifying amoeba that showed up when I raised Sigma. Here it is again, hunting at high resolution. I can't be the only one who finds this genuinely unsettling, right? It's definitely a life form as we've defined them, so it needs its own name. But it's definitely not a little guy, so not the Parvuli genus. So this will now be known as Zerbilex the Devourer. I think maybe that's our sign to change our system again. The last thing I want to do today is make our neighborhood more versatile. Our current neighborhood is essentially a flat disk. When I say flat, I mean that each cell has the same weight in our calculation. For example, these two cells will each contribute their full aliveness value to our aliveness total. But does that make sense from a physical perspective? Intuitively, I might expect a cell's next door neighbor to influence it a lot more than a cell at the edge of the circle. So instead of a flat disk, let's use a Gaussian function to shape our neighborhood like a bell curve. In this visualization, the height of each cube corresponds to its weight in the calculation. So cells near the center of our neighborhood will matter far more for our count than those around the edges. In our code, I've created a function called setKernel. This function first checks how far a cell is from the center of the neighborhood. It then uses that distance to compute a Gaussian weight for the cell, which we'll store for later. It's now later. When we count our living neighbors, we'll now multiply each cell's aliveness by that pre-computed weight. We'll also add the weight to our total neighbors count in order to keep our ratios consistent. By the way, if you're wondering about these variable names, this kind of weighted count is also called a convolution, and the neighborhood is called the convolution kernel. I won't go too much into these because it's really just another name for what we've already been doing, but if you read more about artificial life after this video, you'll definitely run into those terms, so it's good to know them now. Okay, that's enough education, let's go to the game scene. I added in a window in the bottom right to visualize our neighborhood, with red being high weight and blue being low. I also felt like it was finally time to abandon our red on red on red aesthetic, so I applied that color scheme to our whole system to try and get some visual variety. Meanwhile, in our parameters panel, I've added 2 extra parameters for the neighborhoods mu and sigma. As we play with these, we can see the bottom right visualization changing shape. When mu is a lot larger than sigma, we get this kind of ring shape. I want to explore that further, but for our first run, let's leave the neighborhood as a Gaussian blob. And for now, let's just try using the growth settings from the Dosenveni. Alright, moment of truth, let's run it. Interesting. These little jellyfish guys immediately congregated around the spiral I drew. It looks like they like to spawn in high density regions. I wonder if I could draw in new ones with the mouse. I can. God, that's beautiful. These guys need a name, don't they? How about Illustratio Gelata, or Illustration Jelly? By the way, here's what they'd look like in the old color scheme. I couldn't be more pleased with these new colors, they just capture these guys so perfectly. Alright, Let's try playing with our new parameters. When I increase the kernel's mu by a bit, the overall shapes don't change much. However, I am seeing these little jellies popping up now and growing up into larger jellyfish. If we raise the kernel's mu again though, the jellies start to break down. It looks like we've reached the edge of the jelly's survival range. Past this point, we enter a stable dead zone like we were seeing before with the Zerbilex. These dead zones seem to form a large portion of the sample space for this system. Either we hit a stable configuration, or a vanishing one. I ended up tinkering around off camera for a few hours and eventually found this promising space. This space is right on the edge of a stable config, but we can see those small individuals popping up and then evaporating. I really felt like these individuals could be the sequel to the Dosenbeni, but they kept vanishing without a trace. Finally though, I adjusted the neighborhood values just a tiny bit, and this guy appeared. This guy is the first stable individual that I found in the Gaussian kernel, and it's everything that I wanted and more. It moves around, it turns, this particular one is drunk and having a great time, and they have these beautiful intricate bodies with a pronounced central mass and a circular exoskeleton. The shape of the body reminds me almost of copepods, a common species of plankton. But while copepods have antennae, these guys' side structures loop all the way back and seem to function more as extra tails. These aren't aesthetic either. These creatures are largely resistant to superficial damage. If you erase part of the blue exoskeleton, it just regenerates. But if you mess with the side tails, the creature dies. This implies that they do serve some purpose in its anatomy, if only just keeping it stable. Huh. I know it's a bunch of pixels, but I do feel pretty bad about that. There you go, little guy, all better. Body horror aside, the most interesting thing about these guys is how they interact with each other. When two of these guys first collided, I expected them to kill each other like the Dosenbeni do. And don't get me wrong, they do that sometimes. But they can also bounce away from each other. Or sometimes only one even reacts while the other barely notices. But the most interesting thing was when this happened. Both guys lost a tail and they fused together into one being. And then they just carried on like it was normal. This fused version of them was remarkably stable. It moved as one being, reacted as one being, and even stayed together when I tried to destabilize it. If it's not clear in the footage, I'm drawing pixels to try and mess with the creatures, and they're reacting as one entity. You can even see ripples propagating through the entire conjoined body as it reacts. I did eventually manage to split them, and one of the creatures survived for a bit. This proved to be a mistake though, as I was not able to replicate this phenomenon. But the fact that it could happen at all makes this creature all the more interesting. So, with all these data collected and all of this interest, this creature really does need a name so that I can stop calling it this creature. So I'm going to call it the Orbium unicaudatus. Yeah, as much as I'd like to induct this fella into the Parvuli genus, I can't because it's already been discovered. This little guy already belongs to the Lenia. Lenia, meaning smooth, is one of the most advanced artificial life systems out there, and was the primary inspiration for this video. Now that we have our Gaussian kernel, our system has officially entered the realm of Lenia. This means, sadly, that our discoveries from here on out will not be ours, and I can't come up with cool scientific names for them. But it also means that we have a bestiary of little guys already discovered and waiting for us. So for the rest of this video, let's go through some existing creatures that were already discovered in Lenia. But first, we'll need one more change to our system.
The last thing I want to do today is...
Hush, this one is actually the last one. You see, many of these Lenia require a neighborhood with multiple concentric rings, up to 3. Our current neighborhood can only have 1 ring because it's calculated with only 1 Gaussian. So for 3 rings, we'll add up 3 Gaussians. This was a surprisingly easy change to implement. I modified the kernel code to add up 3 Gaussians instead of 1, and I added 3 new parameters to our parameters panel to control their heights. So the first one controls the inner ring, the second one controls the middle ring, and the third one controls the outermost ring. So let's play with these a little, and yeah, that seems fine. Let's try it. Yep, that's about what I expected. Thankfully, we don't have to search these 7 parameters ourselves this time. We have Lenia to look at. So let's try these parameters. And that's Lenia. Or our Lenia, anyway. They're not alive, but they're uncannily close. Today's video brings us up through 2018 in simulated life, but there have been truly amazing advancements since then. Things like conservation of mass, ecosystems, and even evolution. So if you'd like to see more, or you have ideas for what could come next, please subscribe and I'll see you next time. Until then, thank you so much for watching.